Dear students, the last class we discussed Biot-Savart's law and its application. That is, we derived an expression for the magnetic field due to a steady current along a wire. As a continuation of this, we do more problems. That is, the problems based on the Biot-Savart's law. The first question is, find the nature and magnitude of force acting per unit length of two infinitely long conducting wires carrying current I1 and I2 kept at distance d between them. Please look at this picture. Here there are two conductors, conductor 1 through which a current I1 is flowing, conductor 2 current I2 is flowing. The separation between these two conductors is d. Here we have to find out what is the nature, whether it is an attractive or repulsive force. That is the meaning of the nature, and the magnitude of that force. We know the expression for the force experienced by a current carrying conductor placed in a magnetic field B. That force is given by F is equal to line integral I dl cross B. Here B is a magnetic field produced by this current carrying wire. To find out the direction of the magnetic field due to a current carrying wire, we have already explained the right hand rule. That is, if this is a conductor, it is carrying a current I, that is the direction of the current in the upward direction. Fine. Then if you stretch your right hand in this way, that is a thumb in the direction of the current, the curled fingers, this gives the direction of the magnetic field. In this side, that is a magnetic field is coming out of the page, that is denoted by dot. Here the magnetic field is going into the page, that is denoted by the cross. Fine. Similarly, here we are interested to find out the magnetic field due to this current carrying wire. If you hold this conducting wire using your right hand, the magnetic field due to this current carrying wire, that will be in this fashion. Here the magnetic field is coming out, the magnetic field is going into the page, and there will be a large number of circles will be there. That is, this side magnetic field is coming out, and this side magnetic field is going into the page. Actually, this magnetic field is a magnetic field due to the current carrying wire 1. This 1 stands for the magnetic field due to the conductor 1. Fine. Therefore, this B1 means B1 is the magnetic field in which the conductor 2 is placed. B1 is a magnetic field produced by the conductor 1 at the position of conductor 2. Conductor 2 എവിടെയാണ് നിൽക്കുന്നത്, ആ സ്ഥലത്ത് ഉള്ള മാഗ്നറ്റിക് ഫീൽഡാണ് B1. B1 എന്ന് പറയുന്നത് മാഗ്നറ്റിക് ഫീൽഡ് കറണ്ട് 2 മൂലമല്ല, പക്ഷേ കറണ്ട് 1ലെ കണ്ടക്ടർ മൂലം, അതായത് I1 മൂലമുള്ള മാഗ്നറ്റിക് ഫീൽഡാണ് B1. അത് നമുക്ക് കൂടെ എഴുതാൻ പറ്റും. That is the B1 is the, what is the expression for the B1? That is magnetic field due to current carrying wire. The distance d means mu 0. This is due to the current 1 divided by 2 pi. That is, it is at a distance d, okay, where the magnetic field is B1. Therefore, this is 2 pi d. We can write this is a magnetic field produced by the conductor 1 at the position of the conductor 2. So, in this magnetic field B1, the conductor 2 experiences a force. Fine, that is, we have already written here if a conductor is placed in magnetic field B, that conductor is carrying a current I, then that conductor experiences a force. Therefore, in this magnetic field B, this conductor 2 experiences a force. That force is denoted by F2. അപ്പോൾ നമ്മൾ കണ്ടക്ടർ 2 നിൽക്കുന്നത് ഒരു B1 മാഗ്നറ്റിക് ഫീൽഡിലാണ്. അപ്പോൾ ഒരു മാഗ്നറ്റിക് ഫീൽഡിൽ ഒരു കറണ്ട് ക്യാരി കണ്ടക്ടർ, അതിൻ്റെ കറണ്ട് ഫ്ലോ ചെയ്യുന്ന ഈ ഡയറക്ഷനാണ്. കറണ്ട് ക്യാരി കണ്ടക്ടർ വെച്ച് കഴിഞ്ഞാൽ കറണ്ട് ക്യാരി കണ്ടക്ടർ ആയിട്ടുള്ള 2-ന് ഒരു ഫോഴ്സ് അനുഭവപ്പെടും. ദാറ്റ് ഫോഴ്സ് ആണ് F2. സോ ഇൻ മാഗ്നറ്റിക് ഫീൽഡ് B1, conductor 2 experiences a force. That force is F2. Then what will be this force F2? This F2 is equal to line integral. Actually, who is experiencing this force? This force is experienced by the conductor 2. Therefore, this will be I2, then its length dl into where this conductor 2 is kept. It is kept in the magnetic field of first conductor B1. This is the magnetic field produced by the conductor 1. That is, here it is coming out of the page, it is going into the page, and the same magnetic field in the conductor side 2 is this. Here the magnetic field is coming out, the magnetic field is going into the page. Fine. The F2 is the force experienced by this conductor 2, okay, which is lying in the magnetic field B1. That force is written here, and here this dl cross B1, that is the dl cross B1 means it is a vector quantity. That is, I can write dl B1 sine theta. Here theta is angle between this length element and B1. Then if you look at this picture, the length element, that is, this is the length element, and so the current is flowing in this upward direction, and the angle between this length element and the magnetic field, here the magnetic field is going into the page. Therefore, this is going into the page, and the angle between these two, that will be 90 degree. Therefore, this will be sine 90 degree n cap. That is, you can write dl B1 n cap, because sine 90 is equal to 1. Fine. That is, this force F2 can be written as line integral. This line integral means this through the whole length of this wire, total length of this wire is this L. That is I2, which is lying in the magnetic field B1. That is, we are replacing this dl cross B1 by dl B1 n cap. Okay. This dl n cap. This is equal to I2 B1 line integral dl n cap. Fine. If the total length of the wire, that is, this integration of line integral dl means this is nothing but L. Therefore, I can write this integral I2 B1 L n cap. This is the force experienced by the conductor 2. This is its magnitude, and here we are interested to find out the force per unit length, because if you look at this question, that is, it's clear that force acting per unit length is asked. Okay. That is, then force per unit length F2 by L is I2 B1 n cap. This is nothing but force per unit length. Fine. Here, what is this magnetic field B1? Here, the magnetic field B1 means this is the magnetic field produced by the conductor 1 at the position of conductor 2. That is, conductor 2 is kept at a distance d. Therefore, B1 we can write mu 0. This is because of the current in the conductor 1. That current is I1 in this picture. Therefore, this is mu 0 I1 by 2 pi d. Therefore, this force can be written as F2 by L is equal to I2. Instead of B1, you substitute this one. Mu 0 I1 divided by 2 pi d n cap. Now, what is the direction of this force? I can write this is a force F2. There is a force experienced by the conductor 2. What is its direction? To find out of this direction of this force, you can use either right hand palm rule or Fleming left hand rule. I use the right hand palm rule. That is quite easy. That is, keep your palm in the direction of the magnetic field. When the magnetic field is going into the board, then you keep your palm in the direction of the magnetic field and stretch your 4 fingers except the thumb. Stretch all the remaining 4 fingers in the direction of the current. That is, your 4 finger, your thumb in this direction, and except the thumb, the 4 fingers should be along the direction of this current, and the thumb, the direction of the thumb gives the direction of the force. Fine. That is, the conductor 2 experiences a force in the leftward direction, that is towards the conductor 1. This is the direction of the force. Fine. That is, here we can write this force is directed towards the conductor 1. Similarly, we can find out the force experienced by the conductor 1. That is, we can write F1. Okay. Again, let's go back to this picture. If you look at this picture, here the conductor 1 is lying in the magnetic field of the conductor 2. That is, the conductor 2 produces a magnetic field this way. That is, here the magnetic field is, if the current is going in the upward direction, in this direction, therefore the magnetic field here it is coming out. For the right side of this conductor 2, here the magnetic field is going into the page. Fine. That is, the conductor 1 is in the magnetic field, that is where the field is coming out. Here all the places, this is the magnetic field of, that is, this is the magnetic field of conductor 2, and where the conductor 1 is placed. Here we have to find out in the magnetic field B2, that is, in this B2 magnetic field, we have to find out the force experienced by the conductor 1. The current through the conductor 1 is this I1. That is, this I1 experiences a force F1 in the magnetic field B2. That is, you can write that force is F1. F1 is equal to force experienced. This is the force experienced by the conductor 1, which is in the magnetic field of the conductor 2, that is B2, and its length is, total length is L, is n cap. Fine. The B2 is the magnetic field produced by the conductor 2. see this picture. This B2 is the magnetic field produced by the conductor, this conductor at this position of conductor 1. This is at a distance d. It is the B2 we can write. Similar to B1, we can write B2 is mu 0. This is because of the conductor 2. We can write I2 divided by 2 pi d. Fine. This is mu 0 I2 divided by 2 pi d. Then if you substitute here, then this will be I1 mu 0 I2 divided by 2 pi d L n cap. The force per unit length, that is F1 by L, is equal to mu 0 I1 I2 divided by 2 pi d n cap. This is a force per unit length experienced by the conductor 1. Now, what is the direction of this force? To find out the direction, again you look at this picture where the magnetic field, that is, we have to find out the force experienced by conductor 1. Then, in which direction our palm we have to keep? That is, we have to keep our palm in a direction such a way that the magnetic field here is coming out of the ball. Therefore, we have to keep our right hand palm in that direction. Except thumb, other 4 fingers, you have to keep in this direction. This thumb should be alone. This direction. This should be the direction you have to keep your right hand palm. The thumb gives the direction of the force. This gives the direction of the force, that is force experienced by the conductor 1. Fine. Here it is very clear that the force F1 is in this direction and force F2 is in this direction. There is attractive force here. That is, 2 parallel current carrying conductors lies at a distance d experience an attractive force. This is our I1, this is our I2. Then the force is experienced by conductor 1 is this one. Force experienced by the conductor 2 is this one. This is nothing but an attractive force. We know that the equal charges that repel always. But here you see that the like current, and this current flowing along the same direction, is not repelling, but it is attracting. That is, in the case of current, if the currents are parallel, then there will be the attractive force. For direction of this force is directed toward conductor 2. Fine. Now we have answered all the questions. That is, our question was find out the nature and the magnitude of the force acting per unit length of 2 infinitely long conducting wires carrying current I1 and I2. Fine. We're going to find out about the magnitude and direction, and this gives the force per unit length. Force experienced by the conductor 2. Magnitude is this one. Direction is this one. And here also the force experienced by the conductor 1. Magnitude is this one, and direction is this one. Fine. Then you can also check this one if the currents are in opposite direction, I1 and I2. You will see that this force F1 will be in this direction and F2 will be in this direction. That is, opposite current here repel, but the like current or parallel current attracts. Fine. Now let us move to the another problem. This is the problem number 2, and let us go to this question. Find the magnetic field at distance z above the center of the circular loop of radius r, which carries a steady current I. Find this is a circular loop that carries a steady current I, is in this direction. Then whose radius of that circle is circular loop is r. Then at a distance z above from the center, that is here, I have to find out the magnetic field B. Here actually I am not going to solve this problem because you have already solved this problem in the +2 classes, but you must do this as a homework in your notebook. That expression that is quite familiar to you, that is a magnetic field at distance z from the center of the circular loop of radius r is given by is B is equal to mu 0 I a square. Okay, fine. Here we have the radius is taken as r square divided by 2 into the distance square, that is z square, plus r square whole power 3 by 2, and the magnetic field is along the z direction. This is the expression for the magnetic field due to this circular loop at a distance z from the center of the loop. If the loop is kept in this position, like this one, and if its radius is a, then from at a distance x, we have to find out the magnetic field at this point B. This loop carries a current, a steady current I. Then the magnetic field at a distance x, that is at this point P, that the expression is, we can write the same expression, mu 0 I a square, that is radius square, divided by 2 into this x is distance from the center of the loop to the point P where we are interested to find out the magnetic field, that is x square plus a square whole power 3 by 2. Now, if the magnetic field at the center, now we are going to discuss a few cases. That is, in the first case, magnetic field B at the center of the loop. At the center of the loop means, if the point P is at the center means, here the x will be 0. That is, I can draw the loop like this one. The magnetic field at the center B, that is here the, if you look at this expression, here the x is equal to 0 of the point of interest P is at the center, then that is, this is x is equal to 0, then that expression reduces to this way, B is equal to mu 0 I a square divided by 2 into 0 square plus a square 3 by 2, that is, if you cancel out 2 times, it's mu 0 I by 2a. That is, magnetic field at the center of the loop that carries current I is given by 2 mu 0 I by 2a, where a is the radius of the loop and I is the current flowing through the loop. The second special case, that is, the magnetic field at a very large distance from the center of the loop. This point is very far away. Here, then the length or the distance, that is this x, that is x is very much greater than this radius a. Therefore, in this expression, we can neglect this a square because a is very small, then a square is very small, and we can neglect this a square, then this expression will be mu 0 I a square divided by 2 x cube. That is the next one. Magnetic field B at a very large distance from the center of the loop, that is x is very much less than a. Here neglect a square, then that expression finally reduces to this form. It is mu 0 I a square divided by 2x cube. Fine. For the competitive examination point of view, the next discussion will be very useful to you, and let us go to those problems. That is first case that we discussed just now. If this is a current carrying loop whose radius is a, then the magnetic field B can be written as mu 0 I by 2a. Magnetic field as the center of the loop. We are understood to find out the magnetic field center. Second, if this is a half circular loop, radius is a, carrying a current I, then what will be the magnetic field due to this semicircular loop? It's very simple. If the magnetic field due to a full circular loop is this quantity, and this semicircular loop is just half of this circle, that is, we have to take the half of this magnetic field. That is, the magnetic field in the center is given by half of the above magnetic field, mu 0 I by 2a. That is mu 0 I by 4a. Fine, it's very simple. In the third case, here the current is flowing through this conductor is I, and its radius is a. Then we have to find out the magnetic field at the center. So this is circle മുക്കാൽ ഭാഗമാണുള്ളത് അല്ലേ, ഒരു full circle. This is a 3/4 of a circle, and the magnetic field due to this 3/4 of a circle means 3/4 of the magnetic field produced by the full circle. Magnetic field produced by the full circle is mu 0 I by 2a, and this current portion is the 3/4 of the circle. Therefore, this produces a magnetic field 3/4 of a magnetic field produced by a full circle. Every full circle produced a magnetic field ആണ് ഇത്. പ്രസന്റ് സർക്കിൾ അതിന്റെ മുക്കാൽ ഭാഗമായതുകൊണ്ട് 3/4 of the magnetic field. Fine. This is equal to 3 mu 0 I by 8a. Fine. Now, the fourth case, that is a quarter of a circle. This is a quarter of a circle, radius is a, and current I is flowing through the circle. Then, what will be the magnetic field? If it was a full circle, that produces magnetic field mu 0 I by 2a, and the given, the present one is the 1/4 of that full circle. Therefore, this one produces a 1/4 of the magnetic field produced by a full circle. That is, this is nothing but mu 0 I by 8a. Fine. Now, what is the direction of this? These are the magnitude. Then, what is the direction of the magnetic field? To find out the direction of the magnetic field, you have to use your right hand rule. That is, curl your 4 fingers in the direction of the current flow, and stretch your thumb straight, and the thumb gives the direction of the field. Here, to find the direction of the magnetic field, look at this picture. If the take your right hand, and if the direction of the current flow is in this direction, that is, this is a circular current carrying loop, and the direction of the current is anti-clockwise, and curl your fingers, that is in this direction of the current flow. Stretch your thumb in this way, and the direction of the thumb gives the direction of the magnetic field. Okay, that is for this current carrying loop, the direction of the magnetic field is this direction, upward direction. Now, if the current flow is reversed, that is, if the current is flowing in this fashion, that is in the clockwise direction, then we have to curl our fingers in the direction of the current, as shown in this figure. That is, the current flow is this direction, the fingers also the same direction. We have to curl our fingers in this direction. Then stretch your thumb points in the direction of the magnetic field. നമ്മളിങ്ങനെ ഒരു പടച്ച് പിടിച്ചാൽ മതി. കറണ്ട് ഡയറക്ഷനിൽ നമ്മുടെ 4 ഫിംഗേഴ്സും വളച്ച് പിടിച്ചു കഴിഞ്ഞാൽ തമ്പ് സ്ട്രെച്ച് ചെയ്ത് പിടിക്കുക. തമ്പ് നിൽക്കുന്ന ഡയറക്ഷനിലേക്ക് മാഗ്നെറ്റിക് ഫീൽഡ് ഉണ്ടാവും. ഇവിടെ അതേപോലെ തന്നെ തമ്പ് ഫോർ ഫിംഗേഴ്സ് നമ്മൾ കറണ്ട് ഡയറക്ഷനിൽ പിടിച്ചു കഴിഞ്ഞാൽ സ്ട്രെച്ച് ചെയ്തിരിക്കുന്ന തമ്പ് എങ്ങോട്ടാണ് ഓറിയൻറ്റ് ചെയ്തിരിക്കുന്നത്, തമ്പ് പോയിന്റ് ചെയ്തിരിക്കുന്ന ഡയറക്ഷനിലേക്ക് മാഗ്നെറ്റിക് ഫീൽഡ് ഉണ്ടാവും. ഇവിടെ കറണ്ട് ഫ്ലോ ചെയ്യുന്നത് ഈ ഡയറക്ഷനിലാണ്, ദാറ്റ് ഈസ് കൗണ്ടർ ക്ലോക്ക് വൈസ് ഡയറക്ഷനിലാണ്. 4 ഫിംഗേഴ്സിന് ഈ ഡയറക്ഷനിൽ പിടിക്കുക. അപ്പോഴേ തമ്പ് സ്ട്രെച്ച് ചെയ്തിരുന്നാൽ നമുക്ക് മാഗ്നെറ്റിക് ഫീൽഡ് ഡയറക്ഷൻ എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഈ ഡയറക്ഷൻ ഈസ് കമ്മിങ് ഔട്ട് ഓഫ് ദ പേജ്. ഹിയർ I would like to also mention a trick, that is, if you remember this equation, then you can find out the magnetic field due to any circular shape. Fine, that is, the equation is this one: B is equal to mu 0 I by 4 pi a into angle theta. If you remember this equation, then if somebody asks, that is, to find out the magnetic field due to this wire, this is this angle is 60 degree. What is the magnetic field at this point? What is the strength of the magnetic field at this point? If such questions are asked, then you can use this equation. How we can use this equation? That is, you convert this 60 degree into 60 degree is nothing but pi by 3, that is our theta, and in this equation this a is this, so this a, this length is a. Then the magnetic field B can be written as mu 0 I by 4 pi a into theta is pi by 3. This pi and this pi will cancel. This will be mu 0 I by 12 a. Fine. You can apply this equation, this one, into these cases also. Let us check. Using this expression, let us check whether we get this equation or not. We know that the equation due to the circular loop at the center is this: V is equal to mu 0 I by 2a. Then let us apply this equation to this one. Let us check whether we are in this equation or not. That is, the magnetic field B can be written as, here the angle theta means, if you look at this picture, that is, here this angle theta is equal to 360 degree. This is a complete circle. 360 degree means 2 pi. You substitute this theta here. It is mu 0 I by 4 pi a into 2 pi. Fine. This pi and pi cancel, this 2 and this 2 cancel. Then finally you will get this B is equal to mu 0 I by 2. See, both are the same. Then that is using this expression we obtain this. Anywhere here also you can use this expression. That is, you know that magnetic field due to this semi half circular shape, that is mu 0 I by 4 pi a. Then we have to use this expression mu 0 I by 4 pi a into theta. What is this theta? If you look to this picture here, this theta is 180 degree, that is pi. That is the magnetic field B here, mu 0 I by 4 pi a into pi. This pi would cancel. Then you are left with this B is equal to mu 0 I by 4a. See, this is nothing but mu 0 I by 4a. In this way, you can remember these tricks and also these equations. Now you are well trained. Find out the direction and the magnitude of the magnetic field due to any kind of circular shape that carries current I. Okay, thank you very much.